Okay, I think I fixed it. I don't know what OBS did, but it was like, OBS is showing a problem and has decided to shut down. And I'm like, what? Um, so now I have to wait for everybody to come back in. So I apologize for that. I guess I could type this in the chat while people are coming back in. Sorry about that. My broadcasting software just crashed. It should be working now. Oh, I went back to Wednesday. Wow. YouTube, like, completely threw up whatever I had done. I guess OBS really doesn't want me showing you guys Satisfactory. Let me see here. What were we doing today? This is Unit 14, Chemical Equations, and then I edit the rest of this later. What's it called? The title at the bottom of the video should now be working. You might have to hit refresh for that. But yeah, so if you're just joining us, sorry about that. I was playing Satisfactory, and then I, like, alt-tabbed to go to OBS, because I lose my mouse cursor when I'm playing the game. And the entire thing just crashed. Like, it just closed, and a little box popped up that said, oh, this program needs to terminate. And I'm like, what does that mean for my stream? And apparently the answer is it just disappears into the ether. So I apologize. Whoever wanted to see my Satisfactory factory, I hope you were watching for that, like, 5 minutes that I was able to show it, because my computer really didn't like me streaming that. My computer's kind of old, like it's 4 or 5 years old. It's a good computer. I'm patting it right now as I say that because I don't want it to, like, explode or something. It's just now starting to show its age. So I feel like I definitely got my money's worth out of it. I'm probably going to build a new computer in the next 2 or 3 years. Again, patting the computer so it doesn't, like, immediately explode. Let me just get the tablet out here and then click over to this guy. What are we doing today? We are balancing chemical equations and spraying the water bottle at Maya every time she walks around the corner and goes, meow. Because this is now her little game, I guess, that she does, is whenever I sit down to work, she wants me to hug her. And I've been hugging her for, like, the last hour. Pet me, I am soft, she says. And it's like, no, I have to work. Okay. So we've been using chemical equations off and on this entire quarter. This is one of those things where you just slowly have started to see it here and there. And now we're going to finally formally talk about it, about, like, how a chemical equation is represented, what all the numbers and the symbols mean, and stuff like that. Oh my goodness, she's still sitting there. Let me turn this water bottle so that I can get range on it. Oh, she went around the corner. Now I think she's just mad at me. That's okay. On the screen, you'll see a generic chemical equation here. A plus B makes AB. Now, the stuff that we put in is going to be on the left. So we're going to call this the input. And on the right side, I'm going to call this the output. For any reaction that involves chemistry, the amount of input you put in must be equal to the output in terms of mass. So mass, we'll put little brackets around it to symbolize that. Okay. What that means is that if I put 10 grams of A and 10 grams of B in, so we'll write that down, 10 grams of A and 10 grams of B, I better get 20 grams out. If not, my system has a hole or leak in it, or I have violated the conservation of mass, and what I've done is impossible. So we talked about this at the very start of the quarter. We talked about the conservation of mass and how if you do a reaction in a beaker and it makes a gas, and it looks like the gas Or it doesn't look like the gas. It looks like the reaction has lost mass. That loss of mass is due to the fact that some of it was a gas that escaped. So, whenever we do a chemical reaction, we are going to follow the conservation of mass. All of the matter that is added to the container is either used up to produce new matter or is not used up and just sits there. For example, I could do a reaction where I got 10 grams of A and 10 grams of B, and if I only got 16 grams of AB, then I would have an additional 4 grams of unreacted A or B. One of the two. It wouldn't be both, because they would both have reacted with each other if they came into contact. But one of them might have run out first because those atoms are heavier, and so a few of those go a long way. I don't know. So, like, if they were lead instead of, say, hydrogen, you go through 10 grams of lead atoms much faster than 10 grams of hydrogen atoms. So, one of those would be unreacted and then left over. We're going to talk about that a little bit later on in chapter 15, about how we do these types of calculations. But the gist here is that both sides had to add up to the same amount. Now, the next thing that we're going to do is we're going to take our reactions that we see or compose ourselves. So, like, maybe I have, this one's like sodium hydroxide and water or something. Okay, sodium metal. Maybe I want to do this reaction. This is one of the first reactions I showed you in chapter 1 when we talked about facts, laws, and theories. I dropped sodium metal in water, and you watched 3 different variations on it, where one of them exploded in like one of those gray garbage cans as the teacher ran by. The other was like some kids throwing it into a bucket of water in the forest. And then the third one was a little tiny chunk of it in a petri dish. We could describe that reaction in words like this on the screen. Sodium metal reacts vigorously with water to produce sodium hydroxide and hydrogen gas. Now, you would not know what the products are without actually doing the experiment, and that's okay. I know what the products are because I've just seen the experiment done 70 billion times. But if you did know what the products were, or maybe if you didn't, you could write down the first little bit of stuff as a chemical equation and then deduce the rest. Here's what our equation is going to look like when we do that. So I guess I could color code this. So let's see here. So we got sodium metal. There we go. Reacts with water. I'm going to have to erase this because my colors are going to mess that up. To produce... oops, that's the pen, not the highlighter. Ah! Not what I wanted. To produce sodium hydroxide and hydrogen gas. Now, some parts of this sentence are nuanced. For example, I produce these things, so they are the output. They must go on the right side. The things that are used to produce those are the input. They must go on the left side. And we're going to talk about all of these things on the next few slides. But this is the general process. Whatever you put in goes on the left. Whatever you put on the right goes on the... or whatever you get out goes on the right. What does the L mean? We're going to talk about that in just a second. First, let's start giving some terms for the side. So the left side is called the... we're not going to call it the input. Like, this isn't satisfactory. We're not shoving things into a machine. We're going to call them reactants. Reactants are the things that you react. They encounter each other, electron exchange occurs, or they're attracted by other charges, or bonds are broken, etc. When that is done, you get a new thing. That new thing is the products. So reactants are on the left, products are on the right. So in this case, our sodium and our water were our reactants. The reaction began when I introduced those two things to each other. The result was that I made hydrogen gas, which is why it popped in that video. Why is my floor shaking? It's not an earthquake. I think somebody is just downstairs doing something. It startled me, though. The hydrogen gas is what causes the pop at the end of the video, if you remember that back that far. And then sodium hydroxide is just the result of where does the sodium go? It can't just disappear. That would violate the conservation of mass. After each term, we include a symbol to indicate the phase of that compound. Now, you are familiar with the three phases because we talked about them at the very beginning of the quarter, so you know what solid, liquid, and gas are. So that's what the L means. The L means, oh, that is water in the liquid phase. If I did sodium plus ice instead, I would have to be specific, and you can't see that color. Neither can I. Hold on. And I would have to do this instead. That's supposed to be an S, but... So the phase may be important. Usually it's not. However, that being said, phase indicators are often given to help a chemist identify what they should be looking for when they do a reaction. Because a lot of the times, you're doing a reaction that you have not done, but somebody else has. And so if you know, oh, a gas is going to come out, then that could help you know that you've done the reaction correctly, because you could see the gas evolved. Now, what is the difference between liquid and aqueous? Aqueous means that water is involved and has dissolved the compound into separate ions. I have a picture of that in lab number 3, which everybody should have just completed. That's lab number 4. Let me find lab number 3. That's the slides folder. That's close enough. Lab number 3. All right, so what does it mean for something to dissolve into water? If you go to lab number 3 and you find this picture, window capture, is that what I want? Yeah, that's what I want. Ah, I misclicked. There we go. All right. So if I were to dissolve an ionic compound into water, on the left of this diagram right here, oh, you can't see that. I got to click. Over on the left side here, this would be NaCl in the solid phase. So I would write NaCl(S). On the right side here, you can see that the individual ions have broken off and are dissolving in the water. In this instance, I would write NaClAQ. Or more specifically, I would write Na aqueous and Cl aqueous with their charges. Yeah, I figured I was going to answer that with the, I almost said Twitch delay, and with the YouTube delay here. This is what an aqueous compound looks like for ions. They dissolve into individual ions that are surrounded by water. We're going to talk about why the water surrounds them in 161. And if I've set this up right, I should be able to just scroll down here to the next picture. If a compound is molecular, it too can dissolve in water and be AQ. So on the left here, I gotta click over here. In this region right here that I've highlighted with the box, this is my solid. Aside from the part at the top here, let's actually do this. This is my solid sugar. But as you can see, individual molecules dissolve off. They don't dissociate, which is when they break into ions, but they dissolve, and then they're surrounded by water. So when something is aqueous, that means that it is dissolved into individual particles. Now I'm hearing something outside. It must be like some sort of leaf blower. They exist as individual particles, but they don't just disappear or things like that. So the aqueous phase represents matter in the individual molecular or ionic state, but surrounded by water. And the presence of water is actually very important for something called thermodynamics, which we're going to talk about in much more detail in 161 at the very end. And then 162 is pretty much the entirety of 162 is thermodynamics. All right, so that's what all the phases mean. Solid, liquid, and aqueous. I'm sorry, solid, liquid, gas, and aqueous. Now, there are other phases that you could indicate. They're just rare. So, like something like plasma or Bose-Einstein condensate or supercritical fluid. Like, those are all things that exist. We're never going to see those in this class, but if for some reason you did encounter that, you would write that at the bottom in parentheses. The only exceptions that I can think of would be like, instead of just writing solid, sometimes there are multiple forms of a solid. For example, like carbon. Carbon can be diamond, it can be graphite, or it could be Buckminster fullerene. Depending on the form of carbon you have, you need to be more specific. So writing CS doesn't help very much because there are 3 different solid carbons. So what you would do is you put C parentheses diamond instead of C parentheses S for solid. Okay, so sometimes you'll see that too. In the front of these equations are a bunch of numbers. And the numbers represent an important concept that we've already talked about for the mass, the conservation of mass. I need to put these numbers in front of these reactants and products, as I've shown here, in order for the reaction to be balanced. Now, what balance means is very simple. It doesn't violate the conservation of mass. If I put 2 sodium in, I need to get 2 sodium out. If I put 2 hydrogens in there, I can't have any more or fewer than 2 coming out. So if I put 1 in and I got 2 out, that's a problem. So each of these coefficients is placed in front and chosen such that the reaction is balanced. There is always a way to balance a reaction. The numbers may be humongous. However, you're not going to see anything with numbers larger than like 25 or so. And that's actually a very specific exception for when you get numbers that big. In general, most reactions don't go above 6. What our focus today is going to be is to both write sentences into equations. So like that sodium, metal, and water react to form these 2 things and make it an equation. And also to learn how to balance the equation. So that's what we're going to do in this first section. We're going to turn words into a chemical equation. And then we'll balance those equations. Now, whenever you see compounds, you just write their formula into the chemical equation. Now, be careful. I'm using the word compound here. Because for elements, it's a little bit different. So there you go. Compound, write its formula. No problem. You see water, you write H2O. You see sodium chloride, you write NaCl. You see potassium phosphate, you write K3PO4. Great. We're all set. Elements depend on their state. If the element is solid or liquid, it's monatomic. You just write the element and the symbol. So solid or liquid is just the symbol. If the element is a gas, you have to write how you find it in nature. And what that means is that for gases, we find odd combinations of elements based on how other matter behaves. For example, there's a really obvious example out there, and if you take a deep breath, you'll find it. And by find it, I mean you're literally breathing it right now. It's this one. Oxygen is diatomic. That's weird. Only 7 or 8 elements on the periodic table do that. Nitrogen's another one, so you're breathing 2 of them. And of those oddities, almost all of them are gaseous. Or at least they exist in the gas phase a significant proportion of the time, and then are diatomic. Okay? So if it's a gas, you have to write how you find it in nature. Helium is found monatomic, so we would write this if helium was in a reaction. It won't be, don't worry. For oxygen, you do need that too after it. It's very important. Now, how do you know what appears in nature? I'm going to show you a mnemonic in just a second here. But here are the 7 diatomic gases. These gases appear in pairs. H2, N2, O2, F2, Cl2, Br2, and I2. Now you'll notice I've written the silly 7. This is just a mnemonic to help you remember in a second. On the next page, I'll show you a graphic. Now there are other oddities too. For example, phosphorus and arsenic in the gas phase exist in tetramolecular or tetraatomic molecules. And then sulfur is also weird because solid sulfur can actually exist as what's known as rhombic or S8 sulfur. These examples are not worth memorizing, but the ones up here, the silly 7, these I do want you to know. So these right here, ooh, that's really red. I clicked on the wrong color. You should know those 7 and that they are diatomic. Everything else, look it up. Because you're not going to encounter arsenic vapor. And if you do, run away. Like, you don't want to be anywhere near that. The other thing, the other thing to note is that any other gas that is not listed in these bullet points is monatomic. We'll get rid of S8 there. So all the noble gases are monatomic. I can't think of any other gases that aren't the noble gases or the ones that I've listed here. If you were like mercury vapor would be monatomic also. Don't breathe mercury vapor. It's bad and awful. All right, so how do you commit these 7 diatomic gases to memory? Here's how I do it. So the 7 gases are shown on the screen right here. And what you'll notice is that they make... I have the wrong pen selected again. Oh, come on. There we go. They make a shape in the figure of a 7. There they are. So it looks like the number 7 if it was printed out on like a really old calculator. You know, the kind that have like the 8 cells on them that light up. Or 7 cells on them. I don't know how many there are. In addition to there being a shape that resembles a 7, the stem of the 7 is in group 7A. Digital, thank you. Yeah, I couldn't think of the term. And all of this leaves hydrogen over here. Why is hydrogen over here? Well, it's because he's silly. That's why they're the silly 7. I learned this in high school. I have never seen it again elsewhere. I don't know if this is a thing that my brain just made up. I give this knowledge to you. Use it as you will. That's how I remember which 7 are diatomic. Everything else, monatomic or look it up, not worth memorizing. If you wrote P gas on something, only the most, what's the word that I want to use? I didn't want to use the word anal, but that's really where I'm going with this. Like, only the most pedantic, there we go, the most pedantic of chemists would correct you on phosphorus being P4. Because that's basically esoteric. But these chemicals here, these 7, are very common, and it's worth committing them to memory. So now that you know how to write the element or compound into a chemical equation, the only thing that's left to do is to know the phase. And the only way that you can know the phase is to really just do the reaction and see what happens. So what I'm going to try and do is give you that information in the context of the problem. Now, I've heard that one before. It's like Brinkloff or something like that. That is way too complicated for me to remember because that requires spelling. Brinkelhoff, or I don't know. See, me looking at that isn't super intuitive, but seeing a picture works. So whatever works for you. I'm not going to say, like, no, you cannot use Brinkelhoff. It sounds like a goblin's name. Like, I don't give a shit. Do whatever. Use whatever mnemonic works for you. As long as you do remember, don't make a mistake on the test that you just write O by itself. That's no good. You don't want that. All right, so let's do an example here. Aluminum metal is placed into water that contains copper 2 chloride. The solution reacts to form copper metal and aluminum chloride. Now, the phases here are going to be difficult for you to know, but I'm going to try and give you some hints and suggestions here that will get you on the right track. I gotta scroll this up a bit. There we go. And I also need to do this so I can see the problem. All right, so let's write down the stuff that we have. So first, that's not even the pen. First, I'm going to write my reaction arrow. I'm going to put the reactants on the left and the products on the right. Aluminum metal is placed into water that contains copper 2 chloride. So aluminum metal. So I'm going to write the symbol for aluminum. I do a curly L just to indicate that that's a lowercase l and not a capital I. You do not need to do that. Now, because it's a metal, and all the metals in the periodic table except for mercury are solids, we're going to do that. And then it's placed into water that contains copper 2 chloride. Now, my problem that I source this from doesn't really describe how the copper 2 chloride is in the solution. But the intent is for the problem to convey that this is not just solid copper chloride sitting at the bottom in a bucket of water. It is dissolved. And so because it's dissolved, I'll write aqueous. So the key word for this is if you see the word dissolved, then if you see the word dissolved, the phase for that substance is aqueous. Now, the solution reacts, so here's my arrow, to form copper metal. Okay, copper metal. Easy enough. And aluminum chloride. I messed that up. Hold on. Back. Oh, why isn't it working? Oh, I hit the eyedropper, that's why. Wrong button. So AlCl3. And for this one, I gave you very little indication that AlCl3 was aqueous. We're going to describe a surefire way to figure out solid or aqueous in Unit 16 when we talk about solubility. So for now, don't worry too much about phases. Fill them in if you can. All right, so that would be our reaction for the first one. And I think that that's actually the only one I have here for practice, yeah. I found a typo in my slide here. It says Chapter 13, but in reality, there is no Chapter 13. So, Chapter 13 used to be the last chapter in the class, So whenever you see Chapter 13, so cross this out, and this should say Unit 16. I'm using a new textbook for this quarter, which is why my numbers are sometimes strange. And also why I keep saying chapter. All right, so what I want you to do is I want you to take these statements. Oh, ignore that too. That's old hat. I want you to take these statements and turn them into chemical reaction equations like we have shown in the previous slides, okay? Now, putting that information into the chat is going to be kind of difficult. The way that I represent a reaction arrow would be something like this. So Na solid plus water liquid hyphen hyphen caret and then so on. Yeah, we'll do that. So that's how I type stuff into like a text field or whatever. You can use that if you'd like. For the quiz on this content, I will give you a specific uh, syntax to use. Okay. And that will be in the quizzes for you. Okay. So go ahead and write these 3 statements as equations. Type them in the chat when you're done, and we'll go over the answers in just a moment. Yeah, it's gonna probably think that you're spamming the chat, so it'll take a second for it to appear. You'll see it on the screen, obviously, when it appears over here on the feed. Keep going, and we'll go over the answers in just a bit. I forgot to mention that. I typed it in the chat, so if you're reading the chat. For these reactions, don't worry about balancing them yet. That's actually the focus of the next section. Just get the words into formulas with phases to the best of your ability. Okay? All right, I was actually giving people a chance to do another problem that I guess didn't exist because I thought mercury was the second one. So we're gonna go over the answers now because it seems like people are ready for them. I didn't click on this thing. There we go. All right. So these problems I made up, I didn't grab them out of a textbook, so they are hopefully a little more clear on when to write what. That dissolved looks like it's pointing at something, even though it's pointing at something that's technically correct. I'm going to hide it so people don't get confused. So, calcium metal, calcium as a metal, reacts with water, and water is the liquid form of H2O, to form calcium hydroxide and hydrogen gas. There you go. And it looks like most people got that, so good job. All right, let me capture these other two. Get that out of the way here. Hydrogen gas and oxygen gas react violently to form water vapor. What does it mean to have vapor? That means that it's a gas. Now, the reason that water vapor forms and not liquid water is because after this reaction, the stuff is going to be still very hot. So that water will still be well above 100 Celsius and will thus be in the gas phase. It will quickly cool, and then it will become liquid water. But in the aftermath of doing this reaction, you get gaseous water. And then finally, mercury 2 oxide, HgO, will decompose into mercury. Mercury's a liquid. That's okay if you didn't know that. And oxygen gas. Honestly, the phases is just something to like do for practice. I personally don't care about the phases that much. I care much more that you don't put O and instead put O2. Like remembering that to put this 2 in these spots here. That's probably the most important part of this lesson. Second most important part would be putting stuff on the correct side, reactants or products. All right. Ignore this at the bottom. I need to actually delete that because that is from the old text. So when I went back and edited these slides, I missed a slide. I missed 2 slides right next to each other, which is very strange. So in the next section, we're going to talk about balancing equations, but it's like almost, yeah, we're pretty much at 150 or 250. So I'm going to put the break card up. We'll take a 10-minute break. And when we come back, we will balance equations. Let me see if my timer is set correctly. Okay, good. I have a thing I'm doing later that changes what my timer looks like, but I have it set right. So I'm going to do this. I didn't actually pick music because I was playing Satisfactory, and then I crashed Satisfactory. So I will get more Satisfactory music and play that. And we'll see you in just a bit after the break. Hi everybody, we're back. I apologize if you heard the like bling 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 from Google Chat. Steve and I are talking. Steve's another chemist. What am I clicking on? I'm clicking on that first. Okay. I'm all out of order. I clicked on things in the wrong order, and I was like, why didn't it look like what I thought? There's some comments in the chat over the break that you can see now. Regarding phases, phases aren't super important. Like, I realized that that last section had a high emphasis on phases. Now we're kind of just gonna ignore them. I would say that the only phase that you really need to know and understand is like what the difference between aqueous and then other phases is. And so refer back to the picture that I showed you where aqueous is all of the things are dissolved as individual ions. And then the other phases, you could probably imagine them because you've seen pictures of them in Unit 1. Okay. As far as phases are concerned, we're not really going to concern ourselves with them much more. And I'm certainly not going to test you on them because the way that you learn what phases things are is by doing experiments and observing the matter. And in an online introductory level 0 chemistry class, not the best place to give you all the exposure and then demand that you know all these phases. So don't worry if you get the phases wrong. It's not a huge deal. Just know what the phases mean. That's what I'm going to test you on. So you might see a question and be like, what does AQ mean? Choose the choice that best describes it. And that'd be as far as I go with phases. Let's talk about balancing equations. So we don't want to violate the conservation of mass. If you do, then nobody's going to publish you because you are creating matter out of air. You are pulling energy out of the ether. You're violating the laws of thermodynamics, and that's not okay. So you can't do that. So what we need to do is we need to balance reactions that we are given and then do any work we need to with them. Using an unbalanced equation for a calculation will yield the wrong answer. Okay? So always check to make sure your equation is balanced. I would also check to make sure that the equations I give you are balanced. But that being said, I type all of my equations out, and then I do them by hand, and then I edit stuff. What do I mean by balanced? We're going to show what this means in a second. We're going to put numbers in front of each of our terms. So like this reaction right here, I'm going to show you that this isn't balanced. Don't worry about this slide. This slide is just trying to explain what we're doing. What we're going to do is we're going to take inventory of what's on both sides, and we're going to see if we are violating the conservation of mass or we are upholding it. Okay, so the way that you do that is you take inventory. So I'm going to write all of the different elements down. So I'm going to go carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. And then what I'm going to do is I'm going to count them. I'm going to draw a line here to split them into different sides to see what happened before and after. So let's look at carbon. Here's carbon. There's only one, so I'm going to note that. Over here, there's also only one carbon, so I'm going to note that. So it looks like our carbon is balanced correctly. We did not create or destroy carbon. But when I get to hydrogen, I see that there are 4 hydrogen on the left side, but somehow on the right there are only 2. So this equation as written is incorrect. This is not what's happening in a reaction container because that would require us to delete hydrogen. Can't do that. Finally, for oxygen, I've got 2. On the right, I've got 2 and this 1. These are both oxygens, so they all count together. So as you can see, my carbon is correctly balanced. My hydrogen and my oxygen are not. So what do I do? And the answer is, in front of each element or compound, in the blue space that I've written here, I'm going to write a coefficient. And what the coefficients will do is change the balance on each side. If I put the correct coefficients in, I will have the correct number of things on each side. And by doing that, I will attain a balanced equation that satisfies and upholds the conservation of mass. Now, there is a strategy to this. You could just do random numbers. For example, if I'm going to write my number really big here so I can erase it. If I put a 2 here, what happens to the stuff on the left side here? So this 1 would become a 2. This 4 would become an 8. And this 2 would remain 2 because my number here that I have put in front of CH4 only affects the carbons and the hydrogens. Did me putting this number here help us get closer to a balanced equation? You should be able to look at this and go, no, it didn't. It got me worse. So putting a 2 there, not a good idea. So this 2 does not help us. But putting numbers in specific spots can help you. So there is a strategy to this. The other strategy is to look at where elements end up. For example, all of my carbon has to be here. So what does that tell you about the numbers where I accidentally painted some green in? Those numbers better be the same, because if I have a 2 on the left here and a 3 on the right here, my carbon will never be balanced. Oops. Tapped the pad. The other thing that I can look at for, say, hydrogen, is this my, what is this? That's the ballpoint pen. Highlighter. So all of my hydrogen here has to be right here. And all of my oxygen... Man, I cannot see these faint colors here. There we go. All of my oxygen here has to end up both here and here. So as far as my elements are concerned, there are easier choices than others to start with. So if I was going to put a 2 somewhere, what would be my first move? Where would the 2 go? And why would it go there? I'll leave that to you in the chat. So tell me where you think I should enter a number and where. That seems like a great spot to start, right? So if I put a 2 here, and I have 2 H2O, I have 2 times 2 is 4 H2O. I have 2 times 1 is 2 oxygen, but I also have the other 2 oxygen over here, so now I have 4 oxygen total on that side. So now I've got hydrogen balanced and carbon balanced. All I need to do is balance oxygen now. And you're probably saying, oh, okay, well, if I just do this, then it's done. And you're right, everything is balanced once we get to that point. And so this is the correct equation. 1 CH4 plus 2 oxygen makes CO2 plus 2 H2O. When you have everything on both sides equal, the equation is balanced and you're done. Okay? That's our objective here. We want to balance the equation by editing these numbers. So my slide's going to slowly walk you through that, and then there you go. That's what you want to do. Let's do another one. This one's a little harder, so let's inventory and see what we get here. So I got 1 nitrogen and 3 oxygen, because here's my oxygen right here. And on this side, I've got 1 and 2. Now you're going to look at this and go, oh, there is no way I can do anything here because any number I enter breaks nitrogen. Like, I gotta fix oxygen, but I have too many on this side. So if I edit one of these numbers on the left here, so if I edit these spaces, I'm going to increase my oxygen, and that's no good. So that means that there is only one space that I can start with, and it's over here. I have to put a number in this spot right here. If you don't know what to put down, just try something. So I'm going to try. So somebody suggested 3. So let's try 3 and see what happens. So if I do that, I then have 3 nitrogen, because 3 times 1. And then I have 6 oxygen, because 3 times 2. Let's see where this goes. Let's see what happens here. Now, because I have 3 nitrogen on the right, I obviously want 3 on the left. So my next move would be to put a 3 here. Oh my goodness, now she's yelling from the hallway. I was trying to like get Maya to not yell at me, but now she's going to yell louder farther away. All right, so 3 nitrogen and 3 oxygen, but I also have these 2 over here that I have to pay attention to. So now I have this. And now you're looking at this and going, oh, that situation that didn't fix itself super well. So 3 might not have been the best number to try, because we started with too much oxygen on this side, but now we have too little. So if 1 was no good and 3 is too much, or sorry, 1 was too much and now 3 is too little, what would your next move be? Well, mine would be to erase these. And, oh, I got rid of everything. That's okay. And so someone suggested to try 2. And that's what my next move would be as well. So if 3 didn't work, let's try 2, because 3 got us to a situation where there just wasn't enough oxygen on the side. So maybe 2 will work out better. So let's do this. So this becomes 2. This becomes 4. And if I do this, now I need another nitrogen, of course. Like, that's required. But by doing that, look at that. I just happened to get to the right spot. Now, again, there will always be a way to balance the equations. There will always be a set of numbers that results in the balanced equation that you are for your problem. That being said, there is no real you must do this first and then do this second strategy to balancing an equation. There are better moves to make. For example, in this case, this was the obvious starting location. You should start by editing that number because you just had no other number you could edit and get oxygens to be closer to being balanced. Okay? So there are strategies that you can take, but there is no one defined way to balance equations. Okay? All right. My slide is going to overtype this. So let's talk about some tricks that are involved in balancing equations so that you can save some time in doing them. So here are the first tricks that I want to mention. Sometimes you will have a polyatomic ion in your equation. Polyatomic ions, generally speaking, will stay as polyatomic ions. That is, they don't really react or decompose. Now, that's not universally true, but most of the time, and especially for this class, polyatomic ions are pretty stable. They won't decompose unless the conditions are extreme. If they're stable, why do you want to separate them into, say, P's and O's? Just write PO4. And then count the number of phosphates you have. That can really help you if you have a different source of oxygen in your equation. So like PO43 minus and then O2 minus. If those are both in your reaction, counting your O's could be really tricky because you'd have to keep adding them and sourcing them. But keeping them separate entities and thinking of them as puzzle pieces you're rearranging could help you get to the correct answer sooner. We've already talked about this one. If you have an atom, try and determine where it will eventually go. So for instance, if you start with benzene and you make carbon dioxide, you're probably going to have 6 carbon dioxide because there are 6 carbons in each benzene. How many water would you make at the end? Probably 3, because you need to use up all 6 of your hydrogen, and each water uses 2. If you are doing this problem and you end up in a situation that I like to call an arms race, where you balance a number on the right, and then you balance a number on the left, and then you balance a number on the right that's bigger, and then you balance a number on the left that's bigger, and then you balance a number on the right that's bigger, and they just keep growing and growing and growing and growing and growing. What you've done is miscounted. In almost every circumstance, you have miscounted in that situation, and what you should do in that circumstance is just start the problem again and make sure that you are counting more closely. It's really easy to make counting errors in this process. In fact, the whole thing is counting, and counting is probably the hardest thing to do correctly, I would say. At least for me. I make counting mistakes all the time. My guide to you is that if you get really large numbers, and it says 100 here, but even 50, if you get to 50, start over. You're not going to be seeing anything that goes above a number in the 20s or 30s. And I forget if I have an example. I do have the example right here. Perfect. Okay. Here's an example of one of those problems that will do that. So the first thing that we're going to do is we need to write the equation from what is stated here. Now, the reason I have this problem is because there is a special word in here, and that special word is combustion. What does it mean to combust something? I realize you can't see that. Let me move that up. What does it mean to combust something? And if you aren't sure, can you give an example of where you've heard the word in context? Yeah, it means fire, right? So things that invoke fire and burn are combustion, such as a combustion engine. Your car takes gasoline and combusts it. But what is required? Well, you need to pass air through the air filter and into the intake of your engine where it combusts. And in air is gaseous oxygen. So anything that involves combustion must also include oxygen gas as a reactant. Now, spontaneous human combustion will still do the same thing. So, technically, you're not wrong. It will still use oxygen as a reactant, and that oxygen will be from the outside, like in the air around us. Okay? So, whenever you see something combusts, what you should do is you should write that something, and gasoline is a liquid, and that's something else. So combusts our gasoline with oxygen. Now, there is a universal trait that combustion reactions involve or have. And you saw that when we did combustion analysis. Remember what happens if we have only C and H and we combust things? What are the products that we get from combustion analysis? You can look back to Unit 13, where we did that last problem that was, I have a hydrocarbon and I combust it, and these are the things that I get. What did we weigh in the traps so that we could figure out the mass of the products, and thus the mass of carbon and hydrogen? Any idea? I know, Tuesday was so long ago. H2O was one of them. What was the other one? H2O was the hydrogen part. What's the carbon part? CO2. Very good. And this is universally true. You will always get these two things in a combustion. I'm going to write liquid. You could probably get away with writing that as gas. More or less the same thing. Now, something to note here, and I'm going to just switch color here. I'm going to go, so this is for a complete combustion. It's possible to have incomplete combustion, which is where you get this, which is deadly and dangerous. We're not going to worry about that possibility. For the purposes of this class, assume all combustion is complete combustion. I will never ask you to predict an incomplete combustion because it's not really possible. An incomplete combustion will give you a mixture of CO and C and CO2. All right, now that we have our reaction from the statement of, hey, this is combusting, what is the balanced equation? Let's fill in the numbers here. So let's put these dashes here. And those are going to be the spaces that I put numbers on. I'm just going to move this plus over a bit. All right, so let's set up our strategy, same as before. We're going to measure out all of the carbon, hydrogen, and oxygen on both sides. We're going to take inventory. So how many carbon are on the left? Well, they're all right here. So that's 8. How many hydrogen are on the left? Quite a bit. How many oxygen? Just 2. Let's look at the right side here. Only 1 carbon in CO2. Only 2 hydrogen in H2O. And then these O's, there's 2 on the CO2 and 1 on the H2O for a total of 3. Now, this looks pretty obnoxious. This looks like we have a lot of work to do. But in reality, it's not so bad up to a point, and then we're going to cheat. So I'm going to put numbers in to balance the equation. What's our first move? Where do you want to start with? And there's 2 good guesses here. In fact, those are going to be our first 2 moves. H2O. So we'll start with H2O. What number do you want to put in H2O? Or we could do CO2. It looks like people are getting the gist of it. So put 8 in front of CO2. 8 is a good guess. And the reason for that is there's 8 carbon here. I need 8 on the right. I might as well do this. So 8 times 1 carbon is 8 carbon. For oxygen, I have 8 times 2 is 16, but don't forget this 1 hydrogen here. So this becomes 16 plus 1 is 17. That's kind of a crappy number to land on, but we'll worry about that later. All right, now what do I put in front of where? I've got the 8 CO2. Let's work on the... because this guy's done. Let's work on this next one, hydrogen. What number should I enter where? 9 for H2O. That sounds great to me. Because 9 times 2 will be 18. So these are balanced. How many oxygen do I have now? I have 8 times 2 is 16 from CO2. Plus 9 times 1. So I have 25. Alright, so all I got to do is put a number in this blank right here. So that it times 2 equals an odd number. Well, shit. How do I make this work? I can't put a number like that in there. So you might be thinking to yourself, well, maybe I should just, like, start putting other numbers elsewhere. There's an easier way, though. Remember that I said I am going to put numbers into these blanks. I never said the numbers had to be integers. What's 12.5 times 2? Hey, it's 25. This reaction is balanced. And mathematically, it is balanced. But chemically, that doesn't make any sense, right? You can't have 12.5 oxygen molecules because you'd end up with a fractional molecule. That's not a thing that happens. So what we need to do is if we balance the equation and we end up getting a fraction or a decimal or something like that to make it work, what do you think we should do? What did we do in the instance of empirical formulas where we ended up getting a fraction or a decimal? What did we do? Because you couldn't have something like this as your formula. How did we get rid of that? You multiply it by the denominator. So for a half, that would be times 2. So I'm going to multiply this number by 2. But in order to make sure the equation is balanced when I do that, I need to multiply everything by 2. So I'm going to take this, and it's going to become 25. I'm going to take this 1, and it's going to become 2. I'm going to take this 8, which becomes 16. And this 9 becomes 18. So when I do this, all of the numbers on the board here double. So this becomes 16 because I have 2 times 8. This becomes 36, which is 2 times 18. 25 times 2 oxygen is 50. Over here, I've got 16 carbon. I've got 36 hydrogen, 18 times 2. And then I've got 16 times 2 is 32. And then 18 times 1 is 18. 32 plus 18, what do you know? And everything is balanced. So let's tidy up here. Let's get rid of this so it doesn't look like I'm entering a fraction. Our equation after being balanced will be 2 octane plus 25 oxygen makes, oh crap, hold on, 16 and 18. And that kind of looks like a weird 1. I don't want people to think that that's a 4 or something. There you go. There you go. That's the balanced equation. I'm going to put it in a purple box for us. So when I say that you get big coefficients, you should start over, I do mean like going above 50. Because sometimes you get weird situations where you have like 25 oxygens. When you do combustion problems, this is common enough that you should anticipate it. Also, when you do combustion problems, the opportunity to use a fraction exists, and you should do it. But be mindful that you cannot have a fraction in the final equation once you've balanced it, because fractional molecules don't exist. All right, so I think I just print the answers there. So there's the first one where I just entered a fraction as my answer, and then I multiplied everything by 2. I think that was the last example. It was. Okay. Doing that works for any reaction. However, you're most likely to see fractions pop up in combustion. That's not to say it's only for combustion. You can use fractions anywhere that you find applicable. In fact, one of the problems we did earlier could have been solved by using, it was this problem right here. Let me actually clear everything on the screen here. So when we did this before, somebody suggested, hey, let's put a 3 in here. And that totally works. If you do this, because now I have nitrogen 3, oxygen 5, nitrogen 3, oxygen 6. And you might be saying, oh, I need 1 additional oxygen here. So what could I do? I've already got 2 of them if I do that. So what if I did this? That would work. And now I don't want fractions in here. So I would then multiply everything by 2 and get this. And then you could say, well, now I have a number I can divide out by, so I'm going to divide everything by 3. And 636 divided by 3 becomes 212, which was what our answer was before. But you'll also notice, hey, this was a combustion. So these types of situations where you can solve by using fractions do occur in any situation, but by far the most common place that they occur is combustion. But yeah, if you see it come up elsewhere, use it anywhere that it comes up. Feel free to use fractions, because really what you're doing is algebra. All right. Oh, I have homework recs at the end. I gotta edit these slides again, I guess. I sort of breezed over this chapter. So, I believe this is the last slide, so I have a bunch of equations on the board here for you to balance. So I'm going to let you do that. Type them into the chat. We'll go over the answers. I'm going to just write the numbers in at the end. And then if you have any specific problem you'd like me to go over, we'll go over it and do the entire process, okay? So go ahead and balance these equations. Type your answers into the chat when you are done. When I see a bunch of sulfurs turning into SO3, I'll know that we're done, okay? So see you in a bit. So I'm reading the answers in the chat, and the ones I see so far look pretty good, so keep going. almost done, it looks like. We're going to go over the answers in just a bit. Yeah, the formatting for equations typed in is just, it's really obnoxious. No, I understand that. What you're going to see on Canvas is you're actually going to have a bunch of drop-down menus. I'm going to have a reaction it's going to look kind of like this. So blank FE plus blank O2 arrow blank FE2O3. Something like that. And then what you're going to do is each of those blanks will actually be a drop-down menu with a bunch of numbers in it, and you just pick the right number. Unfortunately, I can't type in... I can't make, like, type into the blank problems. Oh my goodness, now she's... Maya... I'm sitting here, and, like, I swear I hear my cat, and she's just sitting here complaining for the entire 2 hours. Trying to hide from me because the water bottle is right here. So you're gonna see problems like what I have on the screen highlighted here. And then there's gonna be drop-down menus, and you just pick the right number. Alternatively, depending on the problem type, I'm trying to remember the problem types now. I might also just have a blank that you type in the number instead. I honestly don't remember how that problem is formatted. Or what problem type that is. I have to look at it. But it'll be something like that. You will not have to type in an equation and hope that Canvas doesn't yell at you because you didn't put a space between your coefficients or something like that. All right, so let me go to the answers here. So where is this guy? So I do these really quickly. So this is 2, this is 4, and this is 3. 2, 2. 3, 6, so this needs to be 2, this needs to be a 3. And hopefully these are matching up with what you got. I'm actually looking through these just to see if anybody else got those numbers. I know this ends up being 6 eventually. 3 and 2. Yeah. This is 3 and this is 2. So this is 2 and this is 3. I have to count these. So 1, 2, 2, 3, 5, 6, 4, 7, 6, 3. There we go. And then this is probably an 8. 24, so 12. Oh, Google is making me... Google is yelling at me. There you go. All right, so hopefully those match up with what you have gotten. And I believe that that is all of chapter, whatever this is, 14. So any questions, let me know. Here's your dancing orc. There he is. All right, and that's it. There are only 2 more units left in the class, and we're going to do one of them on Tuesday. The last one is actually one of the longer chapters, longest, I guess I should say, because there's more than 2. Um, Ogre, Orc, they're all lovable in the same way. Um, what about Unit 15? Unit 15 is calculations involving the mole and these balanced equations. So we're going to take these equations and be like, okay, if I have 10 grams of sulfur, how many grams of SO3 can I make? And you can do that because you know that with a coefficient of 1 here and a coefficient of 8 here, the molar ratio is 1 to 8. It's kind of like what we did with, here's ibuprofen, in 10 grams of it, how many grams are carbon? It's a different way to do it. So that won't take very long to do. Unit 16 is very separate in terms of, like, there's an extra thing that we're going to learn. There's also more calculations that involve the mole. There's a new unit that we're going to talk about, concentration. So 16 is really involved. We have an entire week to cover it, which is week 11. It's going to be after Thanksgiving. There's a lab that involves it, so we do a lot of work on it. Unfortunately, it's at the very end of the quarter, and we're kind of cramming in things for you to do at the end of the quarter. So make sure that you are reading the text and staying ahead, because even though we're on schedule, it sort of all piles up at the end. When will Quiz 8 be out? Quiz 8 will be out. I'm not going to be able to write it tonight because I have something I'm going to be doing for the rest of the evening. I'm hosting a stream on Twitch. So I'm going to try and write it tomorrow. And then it will be posted, and it won't be due on Thanksgiving. I'm going to make it due... I mean, there's no reason why I shouldn't make it due after Thanksgiving on, like, Monday or something, so it'll be due then. So you'll have all through Thanksgiving to work on it if you'd like. If you're like me and you don't want to deal with your family, you could go take the quiz or whatever, but honestly, during a pandemic, I wouldn't be dealing with my family anyway. Stay home, right? All right. I want to thank everyone for coming out. I hope you have a wonderful weekend. Please email me with any questions that you might have, and I will get to them as soon as I'm able to. I'm going to keep grading lab number 3. I'm like a third of the way done with that. But yeah, that's pretty much it. I need to open the correct file here for my little outro jingle. Recent. Uh-oh, why didn't it work? Oh dear. Hold on. I'm just crashing things left and right here. There we go. Let's hit play and call it a day.